Oh, Winter Technical Conference. I don't think these announcements updated. That's more like it. Homework 2 is due on Wednesday. You just turned in homework 1, right? All right. So I haven't yet posted homework 2, but it will be up tomorrow. And my sincere hope is that I'll have to issue fewer corrections for homework number 2 than I did with homework number 1. I guess I'm a little bit rusty on writing homework assignments, and so hopefully I'll get it right the first time and I won't have to give you additional information or updates on that. But the due date will be on Wednesday the 29th. Today what we're going to talk about is some empirical methods that have been developed to calculate the effective pipe friction. So chapter 7 was the theory of resistance when water is flowing through a pipe. Talking about the shear stress, which is the cause of pipe friction. We can't apply that perfect theory to actual engineering practice. It's very uncommon that we would have a direct knowledge of the shear stress. So instead of that, we use the Hazen-Williams equation or a Manning equation, or most of the time, if we care about accuracy and we've got a little bit of calculation ability, we'll use the Darcy Weisbach equation to estimate pipe friction. So we're going to talk about some equations for calculating F to move away from the Moody diagram, and then we may get as far as an initial application into pipe diameter design. Any questions before we start talking about calculating F values? The next part of the course is really among my favorite, just because we get to do some really interesting numerical analyses. So if I get a little worked up and giddy, you'll know it's just because I like calculating F values so much. I can hardly stand it. This is the Moody diagram. You got some practice with this on the homework assignment where you look at the relative roughness, you look at the Reynolds number, the intersection of the two takes you over to the left, and you've got the friction factor. And it's easy enough to do if you know your flow rate and can directly calculate the Reynolds number. But oftentimes we don't know the flow rate that's going to be going through a pipe. Instead, we know maybe a tank elevation and we know the outlet elevation, but we don't yet have a determination of what the flow rate will be. So if the Q is not known, then that means the velocity through the pipe isn't determined. And so the tricky thing is that we may have a lot of situations where we don't know the Reynolds number, and you can't calculate the F value unless you know the Reynolds number. And so it's indeterminate to begin with. And so in situations like that, you have to iterate. You assume a flow rate, calculate an F value, see, does that F value match up with the flow rate that you assumed, and you converge on a solution, and it'll eventually work out. That's an accepted technique. But what makes it a little bit tricky is if every time you calculate, you have to go back to a paper figure and run your fingers along the lines and look for the point of intersection, that can be the weak link that takes a lot of extra time. So instead of using the Moody diagram, the Colebrook equation is a way of calculating it directly. Now, the Colebrook equation is itself a little bit cumbersome, because if you look, the F value that we're looking for is on both sides of the equation, and it happens to be buried in the denominator. On the left side under a square root, on the right side it's under a square root in the denominator and within a log function. So no amount of algebra is going to allow you to isolate that variable F and solve for it directly. It's an implicit equation, which means that what you have to do is you have to guess what the F value might be and check to see what's the result of the left-hand side, what's the result of the right-hand side, and if they equal each other, then that means that your guess value for F is correct. So this is the most accurate way of calculating the Colebrook equation. Now, under these limited circumstances of laminar flow, determining F value is really easy. Remember this section of the Moody diagram where it's just the laminar flow is 64 divided by the Reynolds number. So we do have that to hold on to, but flow is almost never laminar. And so we have to have some way to calculate what the F value is without using the Moody diagram. So here's the first, most accurate across a wide range of water temperatures, because we can adjust the kinematic viscosity that goes into the Reynolds number. This is valid across an enormous range of relative roughness values, K sub S to D. So it's really a flexible equation, but it's best solved with a calculator or on the computer. Now here is a table of some equivalent sand roughnesses. We've seen other similar tables before for different materials. Sometimes K sub S is the variable that's used for equivalent sand roughness. Sometimes it's epsilon. This table is calling it K sub S. So is this equation for the Colebrook equation. But you maybe would see it with an epsilon and just know that that's talking about the equivalent sand roughness relative to the pipe diameter. Now just to show you how this equation needs to be solved with Excel, let's consider the case of what if we had water flowing through a pipe that has a diameter of 136 millimeters, and what if that's galvanized iron. So the material defines the equivalent sand roughness, and then the flow rate of 200 liters per second is going to allow us to calculate the flow velocity. So the first thing, anybody have a marker? Oh, I forgot. Oh wait, I do. I've got a marker. All right. Didn't think I did. First things first, we want to have the cross-sectional area from the diameter. So pi d squared divided by 4 tells us that for this pipe, the cross-sectional area is 0.01453 square meters. And then the velocity of the water through the pipe is Q divided by the cross-sectional area. Remember, we want to know the velocity because we need the Reynolds number. Reynolds number is one of the terms that goes into the Colebrook equation. Okay, so our Q is 0.20 cubic meters per second. The area is 0.01453 meters squared. So the velocity through this pipe is 13.77 meters per second. It's moving really quickly. That's fast-moving flow. So the Reynolds number is this velocity, 13.77 meters per second, multiplied by the diameter of the pipe, 0.136 meters, and then divided by the kinematic viscosity for water, 1 times 10 to the minus 6th meters squared per second. Okay, so that Reynolds number is 1,872,413. Let me show you how we could set this up to solve it in Excel, to find the friction factor, like what F value applies. We could use the Moody diagram if we wanted. We could find the relative roughness, intersection of the Reynolds number, take it over to the left side. But just for practice, let's try the Colebrook equation. Now this isn't the spreadsheet that I mentioned earlier as being available online. This is a different one, but all it has is, let's put in our K sub S, let's see. All right, the K sub S for this was 0.15, thank you. 0.15, the diameter 136, so the Reynolds number was, we already calculated that, but we'll just double check here. So it is 13.77 times the pipe diameter, 0.136, divided by the kinematic viscosity, 1 times 10 to the minus 6th. All right, so 181.87 million, just like we'd gotten before. We don't know what the F value is, so we'll start with some guess. At the lower end of the spectrum would be 0.008, and then we just go up from there. And we'll do a lot of different versions of what maybe the F value is. And so we'll see the left-hand side of the equation is 1 divided by the square root of our F value. So when f is this value, then the left-hand side of the equation is 11.18. When f is this, the right-hand side of the equation, this is going to be a little trickier to type in, but we'll be able to get it. So equals negative 2 times the log of k sub s. So clicking here, and I'm anchoring the reference. Oh, I've already renamed this cell k sub s. So you see how it says k sub s instead of B3?
How do you do that?
You do that by up here. So see how this is tacos. Right here, this one is called A10. So you can rename any cell what you like. And so I named this cell K sub S. This one I called D. This is called RE.
That is very nice.
Okay, so equals negative 2 times the log of K sub S divided by 3.7 divided by D. Do you see what I did there when I divided twice? That's to avoid having to put in parentheses. Like I could have also said K sub S divided by 3.7 times D, close parenthesis, but it's fewer keystrokes if I just say divided by D, divided by 3.7 divided by D. And it's numerically equivalent. So 2.51 divided by Reynolds number times the square root. Now this is where I finally reference the value that's here. This is the f value. Okay, so I need to make sure that I've closed all the parentheses. And so, looks like I've got some issue. The problem is I don't have a Reynolds number. So the Reynolds number was equals the velocity, 13.77 times the diameter, this divided by 1,000, divided by 1e negative 6. I've got the K sub S in millimeters, and so the D is also in millimeters, because if I put it into this, the units have to be the same. You know, if K sub S is millimeters, then diameter has to be millimeters. So here in the Reynolds number, when I was using the diameter to calculate the Reynolds number, I was sure to divide the given diameter of 136 millimeters, dividing that by 1,000, make sure it's in units of meters. So any questions so far? So left-hand side of the equation and the right-hand side of the equation right now do not equal. So it's not correct. Let me just make sure that I've got the formula in here the right way. K sub S divided by... All right. So the difference between the two is not yet minimized. What we want to do is drag this down and find out at what point, at what point is the difference minimized? Like which f value is corresponding to the crossover point. So you'll notice that the left-hand side and the right-hand side are getting closer and closer to equal, but it's right around here that they're pretty close to equal, so that's giving me an idea of what is the f value. And then I can get even a little bit closer with goal seek. And so my goal is I want the difference to be equal to 0. And so what it can change is it can keep changing this f value until the difference is 0. So you maybe remember that in data, what if analysis, goal seek, my objective is set this to 0 by changing the f value. All right, so this is the friction factor, and that's a lot more precise than we'd be able to get it off of the Moody diagram. You know, the Moody diagram we can maybe do to 3 digits, but certainly not to 5. So the f value that makes the left-hand side and the right-hand side equation of the equation equal to each other is 0.025 0.2012. That's not terribly convenient, I mean, but it's really, that's the most accurate way to calculate the F value. Fortunately, there is a more accurate way that you're going to take a look at in just a moment. I'll mention that you don't have to use Excel to solve the Colebrook equation. You know, I've had students use their Casio calculator before, and if you are able to put this equation in without making a mistake, the Casio will solve for F. It takes it about 25 or 30 seconds though to do it, but it will, depending on how good your initial guess of F is. We don't really have the time to watch the entirety of this video, but do the links come through when you print the PDFs? Like when you, obviously you can't just touch the piece of paper, but you know, like if you have the PDF, are these hot links in the PDFs?
I don't think so.
No? All right. Well, if you want to see a real calculator solve the Colebrook equation, yes, I'm throwing it down here. The Casio that they taught you to use in 111, that's not a real calculator worth owning. It's garbage. So a real calculator like the HP has a really powerful way of entering in the equation in a graphical method.
That's awfully... Okay then.
Yeah, so if you want to watch the video, just solving Colebrook equation for Frichter factor, it's an emulator that illustrates how to type the equation in a graphical way. Like the advantage, without watching the whole video, I'll show you. You can actually type an equation the way it's supposed to look. And that's the main complaint that I have with the Casio is when you're typing in an equation, it certainly doesn't look like that, right? You have to use like A, B, C, D. Number one, you can't actually call the variables anything you want. And number two, it's not like graphical. You're counting your parentheses and everything, and it's a real nuisance. And so if you want to spend the $100 and buy a calculator that is worth owning forever, I think the HP 50G is a pretty good one. And then you'd have the added advantage of being able to put in the Colebrook equation and just solve for F that way. But it really doesn't come to that because there's an approximation for the Colebrook equation that isn't implicit. Remember, implicit is when the variable's on both sides of the equation. The Jain equation is direct rather than being implicit. And what you can do is put in the K sub S, the D value, your Reynolds number, and within certain conditions, you know, within a range of Reynolds numbers, within a range of relative roughnesses, it will give you an accurate approximation of the F value. So this is an important equation, and I'd like you to get some practice with it. Let's see how good it does under these conditions. First of all, is the Reynolds number within the acceptable range? So if it's from 5,000 to 100 million is when the Reynolds number, and our Reynolds number is 1 million. So, you know, our flow conditions are within the acceptable Reynolds number range. What about the relative roughness? Well, our K sub S was 0.15 and the D is 136. So 0.15 divided by 136 is 1 times 10 to the minus third. So the relative roughness is also within the acceptable range. So we should be getting an F value that's pretty close to what we saw with the Colebrook equation. So this is the exact F value. What I'd like you to do is use the Jain equation to find out what's the approximate F value.
Yeah.
Okay, so Colebrook told us that in these conditions our friction factor should be 0.0201, and then Jain equation said 0.0203. So that's awfully close. Yeah, very good agreement between the Jain equation and the Colebrook in the middle of the range like we are. Like if you're further to the edge of what's allowable, like if you're closer to the upper or lower limit of the Reynolds number, then it doesn't agree as tightly as it does here. But because it has a pretty good agreement, the general rule of thumb is that you can use the Jain equation this semester unless I specifically tell you to utilize some other approach for F. Like if I told you I want you to use the Moody diagram or that you should definitely use Colebrook, then use those other methods. But Jain is good enough in any other cases. Okay, so what this does is it's telling us the F value for certain flow conditions. And remember, the reason why we want to know the F value is it's our empirical method for approximating the effect of pipe friction. It's how much energy we're going to lose as the water is moving through the pipe at a certain velocity. Any questions about the Jain equation or Colebrook? There's also, yeah.
Can you use the solver function on your Cassius? Because I did it and got the same from both.
So you're asking, could you use solver for this?
No.
Or for Colebrook?
Colebrook.
Yeah, you can use solver for Colebrook. On the Casios, I think it'll take some time for it to converge, though. So like if you put it in and it doesn't immediately give you an answer, that doesn't necessarily mean that you did it wrong. I think it'll take 20 or 30 seconds, but some people have successfully made it out the other side with all the commas in the right spot and the parentheses in the right spot, and it did work. Okay. But you can always use, like when you're working on your homework, you can use Excel. Just show your work. It is possible to show your work with Excel. If you're providing the spreadsheet, the equations are there. You can put notes in the spreadsheet that helps the grader to see what you did. If you submitted something like this, it would be pretty clear that you're doing a left-hand side, a right-hand side. You're looking to see if it's equal. I mean, I would be able to look at this and know that you were solving for the F value and that this was the place at which the two were equal. So you don't have to do, like you could also do it by hand. The brute force approach is with your calculator. What is 1 divided by the square root of your guess of F? And then on the right-hand side, with your calculator, type all that in. And then you manually say, all right, well, that was too low. I'll try a higher value of F. So there's lots of different ways to do it. All right, so Colebrook, really accurate. Jain, pretty accurate and a lot more convenient. Blasius equation is really easy to use, but only accurate for Reynolds numbers up to 100,000. So not a lot of practical application for a drinking water distribution network. Okay, you've seen situations before where you've got an elevated water tank taking water to a building. And in a situation like that, if you know that the elevated tank is open to the atmosphere, you know that it's not pressurized, and water is going towards a building, and there's maybe some required pressure at the building. So hopefully this is seeming pretty familiar. You had a homework in the same situation. The elevations are known. In a case like this, if you know the elevation differences and you know the difference in pressures, you can estimate the head loss that is going to occur through that pipeline. So this is just rearranging the energy equation to solve for head loss, and we're neglecting the difference in velocity heads between the 2 points, because velocity heads are relatively minor. This is a pretty good approximation for how much head loss there is through the pipe. In a situation like this, you may know what the flow rate needed is downstream by looking at the number of people living in the building, for example. And if you have an idea of what their behavior patterns are, how many washing machines there are in the building, do they all work on the same shift where everybody's getting ready to leave for the morning at the same time? And those human behavior patterns are important when you're doing a demand estimation. So let's just say, for instance, you've gone through that process and you know the queue that has to be delivered to that building. The unknown in a situation like that, where you know the queue and you know the head loss difference that's going to occur. The unknown is how big of a pipe is needed to convey the flow. And what you can do is you can think of this H sub F is the driving force. It's kind of the energy you have available to push the water through the pipeline and get it to the place where it wants to go. It's your currency. And so H sub F, this difference in the energy at the potential energy in the tank and the energy downstream that exists partially as pressure, partly as elevation, that H sub F is what's driving the flow through the pipe. So if you've got a certain amount of pressure and a certain amount of elevation, then you've got the energy that's going to be moving the flow. So a small pipe is going to have more head loss. Because if you look at the Darcy Weisbach equation, remember that equation is H sub F is FL V squared divided by D2G. So let's say that we're trying to get a certain amount of water to the building. If you have a small diameter pipe, what is the velocity going to do for a certain steady flow rate? Small pipe, big velocity. Okay? So if you have a big velocity, then that means you have to have a big H sub F to push it through the pipeline. So in other words, a small pipe, you're going to need to have a very high tank, a very high elevated tank to have enough energy to push it through the pipe and overcome the resistance that's associated with a small diameter pipe. On the other hand, if you have a really big pipe, it will be easy for the flow to get through that pipeline. There will be less head loss for a certain velocity. And it's especially true because velocity is squared and pipe diameter is in the denominator. So a small d is going to be driving up the velocity, and then is going to be a small number in the denominator, so it's going to kind of amplify the effect. So this question is, how big does the pipe need to be? We're balancing competing factors. On the one hand, if you have a pipe that's too small, then you won't be able to get the required flow rate to the building. But if the pipe is too big, then there's a cost associated with that. You know, the material costs and the installation costs, and you know, welding it all shut and placing it into trenches is more costly the larger the pipe is. So the process of trying to design the pipe is looking at the head loss that's available and estimating for a certain material what is going to be the velocity for a given diameter and how much head loss there will be. So if H sub F is a known and the unknown is what diameter is required, we can rearrange the Darcy Weisbach equation for a circular pipe to look like this. So here, instead of V in the Darcy Weisbach equation, what we did is we substituted in Q, because here in the Darcy Weisbach equation, remember that V is Q divided by area. So we could also say that H sub F is FL Q squared divided by D2G A squared. So that's an acceptable well, it's not an approximation, it's the same thing, where we're just swapping out what we have for the V. And the reason why we make that substitution is that, you know, in this illustration, we know the Q, the water flow rate demand that has to go to the building, but we don't know what the velocity through the pipe is going to be until we know the diameter of the pipe. So there would be two unknowns and only one equation if we didn't make the substitution. In this, we have the Q, that's how much water they need at the building. L is the length of the pipe between the tank and the building. H sub F is the head loss difference that was defined in this equation. So it's the difference in the pressure head and the difference in the elevation between the two spots. Of course, G is a gravitational constant. Pi is just related to the circular geometry of the pipe. and of course F is our friction factor. So we've rearranged the Darcy Weisbach equation to solve for D. And so it's almost like ready to use and size the pipe, except for the fact that F responds to the flow conditions. It responds to velocity. Remember that F is a function of the Reynolds number, and the Reynolds number isn't known until we know the velocity, and so all of this is kind of interrelated. The F depends on the D. But there's a way around that. There's a process that we can follow to find out how big the pipe needs to be. The most accurate implicit approach to solving this is your first taste of how things go in hydraulics, where if you have two unknowns in an equation, you just start off by guessing one of them. You guess a reasonable value for one of them and see like what follows if you make that reasonable guess. So you start by assuming an F value. The lower range of F is 0.008. The upper end, the highest F value you typically see, is 0.038. So you just pick something in the middle maybe, and then you find out what diameter would be required if that was the F value. And so once you have that diameter that would be required for the pipe to convey the flow, so this is going to tell you, how big the pipe needs to be to make sure that the friction losses don't exceed what you've got available. You find out, all right, well then what would be the velocity of the flow for that diameter, and therefore what's the Reynolds number? And so what you can do now is check to see if the F value that you guessed is accurate. So you start with an assumption and then you check the assumption. And of course it's not going to exactly match up. It's not going to be this miraculous guess where you exactly guessed what the F value was. What you have to do is you have to incorporate a new updated F value into this formula, and you may need to slightly change the required diameter. And so you go this process of assume something, calculate, you check the assumption, you correct the assumption, and then you recalculate. And so you keep bouncing back between recalculating and correcting the original assumption. It makes more sense when you actually do it than seeing it as a bulleted list. But any questions so far? We're going to do that process. We're going to take a look at this scenario. If we have a known pipe length and we know that the H sub F that's available is 45 meters, and so hopefully by now you have a sense what that means is it's kind of the driving force that's pushing the water through the pipeline. So we've got 45 meters of head to cause the flow to go through there, and what we want to make sure is that there's 300 liters per second going through the pipeline. But what we don't yet know is the diameter that's required to achieve it. Can it be a really small diameter pipe? Does it need to be a big diameter pipe? It's going to be made out of cast iron, but how large of a pipe is required? So what we'll do is we'll assume some F value. We'll start with a guess. We'll put it into this equation. Then we're going to calculate, based on the guess, what would be the Reynolds number, what would be the relative roughness, and we're going to adjust. We're going to use a new F value. We'll use the Jain equation just to simplify. We won't utilize Colebrook. We'll do the easy route and calculate a new F value, and then repeat the cycle over again with our updated F value. Okay, now this is where we will start with the template file that I put onto Blackboard. And if you don't want to follow through right now, it is available later on. You can just download it. But that is what I'm going to be starting with. And the reason why I have that template file is it just has the formulas and so on right on the screen for us. And it kind of is implying the steps that you need to follow right there on the screen. All right, so the flow rate, it says we want to achieve is 300 liters per second. So 0.3 cubic meters per second. The cast iron has a roughness of, remember, the K sub S and the D need to have consistent units. And so what I'm going to do is I'm going to use K sub S in meters. So it's 0.26 divided by 1,000. and now that's in meters. The length of the pipe is 40 meters, G 9.81. The H sub F, the head loss that we know is going to occur, the driving force that's pushing water through that pipe is 45 meters, and then the kinematic viscosity, which we'll refer to when calculating the Reynolds number, is 1 times 10 to the minus 6th meters squared per second. Okay. So some assumption for an F value. I'm just going to guess a bad guess. Like a good guess would be 0.02. I mean, like most F values are about in that range most of the time. But just to prove to you that it can still converge to the right answer even with a bad guess, I'll let it be 0.015. So a little bit lower than would be realistic. Okay, so with that guess, now I'll use the formula to calculate what diameter would be required if that's how rough the pipe was. So equals 8 times the length, anchor that reference, times the flow rate, anchor the reference and square it, and multiply by F. So here's our assumed F value. I'm not anchoring that. Okay, now divided by H sub F, anchor the reference, times G, anchored, times pi squared. Pi squared. Okay. And then all of that is to the power of 1 divided by 5. No, I think I may need even an extra set of parentheses there. Let's see. Yeah, all right. Now I've got it. So this is the diameter that would be required if this is how rough it was. But let's see if that's really true. Like, all right, for our known Q of 0.3 and the pipe area, so based on this diameter, then the pipe area is pi times d squared divided by 4. And so the velocity would be Q divided by the area. So this is all now like a what if. The water would be flowing 15 meters per second if this was the diameter. Well, what would be the Reynolds number if the water was going that fast? It would be this velocity times the diameter of the pipe divided by the kinematic viscosity. Okay, so this would be the Reynolds number in that scenario. And so what is the F value, this new F value? Now that we have an estimated value for the Reynolds number, let's use the Jain equation to come up with a newer and improved F value, a better, more accurate F value that isn't just pulled out of thin air, but this time is based on an actual equation. So equals 1.325 divided by the logarithm of K sub S to D. So here's the K sub S divided by 3.7 divided by this diameter, okay, plus 5.74 divided by the Reynolds number to the power of 0.9. And then that needs to be squared. You're going to get a lot more comfortable this semester typing in complicated equations into Excel. Like, you'll just get proficient and a little bit less intimidated with having to translate an equation into the way it ought to look. Now, me having said that, look, it'll probably give me an error message or something, but let's give it a shot. Okay, no, it actually turned out to be right. So this is a more accurate guess of what the F value would be. So just to check and see, are we converged yet? You know, like what's the percent difference between my initial assumption? So percent difference is going to be the initial guess minus, oh, let me put parentheses. So the initial guess minus the update divided by the more accurate one times 100. So my initial guess was 33% too small. So I'm not converged yet. I'd like that difference to be a lot smaller. But the good news is that for the second time around, it gets progressively easier because we can repeat equations and so on. So my new assumed value of f is going to be this one that I just calculated from above. Okay, so what diameter should it be? You know what I'm going to do is I'm just going to copy and paste. So I'm going to copy that equation, and then let's see if I can just paste it. No. Control C, Control V. All right, so everything is anchoring that original stuff that isn't changing, except for now it is looking at my new f value. So based on this new improved f value, instead of having a diameter of 0.158 meters, now I know it needs to actually be a little bit bigger because the pipe's not that smooth. My initial guess was unrealistically smooth. It was assuming that it had this really low f value for the pipe. The pipe isn't that smooth, so the pipe needs to be bigger than I originally had come up with. And so, well, what's going to be the flow rate based on this new pipe diameter? Let me do that same thing as above. Let me just copy all of this, Control C, and paste, Control V. Oh, I've done something wrong. So let me get the right flow rate reference. So Q, there's the Q. Is this giving me area? Yes. Velocity is Q divided by area. Reynolds number. Good. And so now a new f value. Let me do the same thing. This is my new f value. Control C, Control V. Nope, something went wrong there. There was a reference that wasn't anchored. Yeah, I bet it was this one. Let me move this down. Sometimes copying and pasting works great. Other times you have to debug it a little bit. So so logarithm of k sub s to d. Yeah, the k sub s wasn't anchored the way it ought to. So let me move this back up to where the k sub s should be. There it is. All right, and I'm going to put $signs there so it doesn't move next time I refer to it. Diameter is going to change. Reynolds number is going to change. All right, now this is the exciting part. If it works, then our percent difference should be a lot smaller than it was before. Remember, our percent difference during the first iteration was 33%. So now our percent difference, it was changing a lot less than it was the first time around because we had a better guess to start with. It only changed 2% this time. You know, it went from 0.022 to 0.022. You know, a relatively small. So we could do it one more time and get it within 1% accuracy. So that is the process. Oh, I've kept you 2 minutes late. I'm going to pay you back with interest on Friday. Just you wait. With interest. All right. So before I do let you go, though, my hostages, let's just see. Homework 2 is due on Wednesday. I'll upload that to Blackboard tomorrow. And then on Friday, we will finalize this example and go from there. Have a good day.